My name is Clingman, and I'll be giving the representation presentation. Following is joint work with Lynn Moser, and this video has been submitted for CT20 Arrow 21. Before we get started, a few words about me. I'm currently studying a PhD in mathematics at Johns Hopkins University. I expect to graduate in 2022, and I'm interested in formal category theory, higher categories, homotopy type theory, computer implementations of these sorts of things, and general programming. For more information about me, please visit slil.xyz. And if you'd like to talk about this talk or send me questions or comments, please don't hesitate to reach out to slil@jhu.edu. The slogan for today's talk is that properties and structures in an object are the same things as representations. And so by understanding representations, we can understand a lot of category theory. By a representation of a presheaf F, I mean a pair of an object, I in C, and a natural isomorphism, rho, from humming into that object to the presheaf F. Our understanding of representations is bolstered by the classical representation theorem, which, for a fixed presheaf F, says that representations of that presheaf are the same things as initial objects in the category of elements of F. The category of elements of F is a well-studied and understood structure. An example of a corollary of the representation theorem is the familiar characterization as limits as terminal objects in the category of cones. An example derivation of this characterization is given below. For a diagram F to have a limit, we may check that that is the same thing as the presheaf of natural transformations out of a constant diagram having a representation. By the representation theorem, this is the same thing as there existing an initial object in the category of elements of that presheaf. Finally, we may check by hand that the category of elements of this particular presheaf is none other than the opposite of the usual category of cones over F. That is, F has a limit precisely when there is a terminal object in the category of cones. Another familiar corollary of the representation theorem is the characterization of right adjoints. A functor L has a right adjoint if and only if there exists a terminal object in each slice L over D for each object D in D. The motivating question for this talk then is, what does all of this look like in 2D? Well, using the previous characterization of limits as terminal objects, we can derive a test to probe for a suitable two-dimensional representation theory. Consider the following chain of double implications. Given a two-dimensional diagram, we can check that it has a two-dimensional limit if and only if the appropriate collection of two-dimensional natural transformations forming a two-dimensional presheaf has a two-dimensional representation. Starting at the other end, we can check that two-dimensional terminal objects in a two-dimensional category of cones for this two-dimensional diagram are the same things as two-dimensional initial objects in the two-dimensional category of elements construction. Thus, by comparing the first statement to the last, we can probe for the red double implication, that is, the two-dimensional representation theorem. The question is then, are two-dimensional limits the same things as two-dimensional objects in a two-dimensional category of two-dimensional cones? In our paper, two limits and two-terminal objects are too different. Lynn Moser and I show, in fact, all such theorems are false. Our results are summarized in the two below tables. In particular, this means that there cannot be a passage as indicated below. And the culprit, it turns out, is the two-dimensional category of elements construction. Does this mean that there is no two-dimensional representation theorem? In fact, there is, but in order to state it, we needed to introduce a novel functor from the category of double categories to the category of two categories. This functor V sends a double category A to the two category V of A, whose objects are vertical morphisms in the original double category, and whose morphisms are squares in the original double category. Using this functor and some appropriate definitions, we were able to prove the equivalence of the following three things. 1, the object I is double biinitial in the double category A. 2, the object I is biinitial in the horizontal two category of A, and the pair I, vertical identity on I, is biinitial in V of A. 3, the pair I, vertical identity on I, is biinitial in V of A alone. That is, comparing 1 and 3, we see that our novel functor V is enough to detect double biinitial objects in a double category. Using some supporting theorems relating double category of elements to birepresentations, as well as some lemmas about slice constructions, we were able to finally prove a satisfactory version of the two-dimensional representation theorem. Given a normal pseudo-functor f from C up to cat, the following three things are equivalent. 1, f has a birepresentation, that is, a pseudo-natural adjoint equivalence as displayed. 2, the pair II is biinitial in the usual two category of elements of F, and the pair IDI is biinitial in the here novel two category of morphisms of F. This two category of morphisms is definable in terms of V, our novel functor, as well as the double category construction. 3, the pair IDI is biinitial in the category of morphisms of F alone. That is, reading the implication between 1 and 3, we see that a pseudofunctor has a representation if and only if there is a biinitial object of a certain form in the two category of morphisms. We then applied this result to two-dimensional limits to derive a correct characterization of two-dimensional limits as certain kinds of two-dimensional terminal objects, as well as to rederive a familiar result concerning biadjunctions. We were able to specialize our result to the case of the presence of tensors by the category 2 and obtain a substantial simplification of the above theorem in that case. For details on our work, please see the paper Biinitial Objects and Birepresentations Are Not So Different. Thank you for your attention.